So here's the format of today's talk. The worst talk of my life. It's a little bit different than what I had planned in the abstract. We're going to start with a really bad talk. It's not an actual talk that I gave, but it's inspired by all the crappy talks I gave when I was in your shoes, and I didn't know any better. And so I tried to kind of put it together to illustrate the key failing points that I've had to go through. Next, we're going to have a discussion about what went wrong. So make sure you take notes of what you didn't like, and that's totally objective as well. Sorry, totally subjective. I still don't know the difference between objective and subjective. It's an English thing. So it can be very subjective. Okay, like, you didn't hear me well, or which could be a fact, right? Then after the discussion, if time allows it, we'll repeat the talk in a slightly better delivery inspired by our discussion, okay? So it's supposed to be an 8-minute talk, so I put on a timer, and I'm gonna stop bluntly exactly when that timer hits 8 minutes, okay? All right, are we ready? Okay. Good morning, everybody. Welcome to my talk today, the theoretical foundations of low-cost fast projection methods for constant density incompressible Navier-Stokes equation, Navier-Stokes solvers using explicit second, third, and fourth order Runge-Kutta integrators on structured staggered uniform grids with second order finite volume discretizations in space on massively parallel computers. My name is Tony Saad. I'm assistant professor of chemical engineering at the University of Utah. This work was supported by the National Science Foundation and NSF and the Department of Chemical Engineering. Today's agenda, we are first going to talk about the introduction and the background. Second, we are going to talk about the governing equations. Third, we are going to talk about the numerical method that are used in this work. Fourth, we are going to talk about the projection method. 5, literature review. 6, the new theory that we are going to propose today. Some results of the new theory, conclusions, and then questions and answers. Introduction and background. The Navier-Stokes equation govern the motion of fluids. They are complicated coupled partial differential equations. Analytical solutions are available for some simplified limited cases. And computational fluid dynamics is a method that solves these equations numerically on computers. And the projection method is a way to solve the equations. These are the governing equations. This is the continuity equation, div u equals 0, and you have 3 momentum equations. The first term is the unsteady term, x momentum, and then x convection term, x pressure gradient, x gravitational term, and x diffusion term. And then the y momentum equation, you have the y unsteady term, y convection term, y pressure gradient, y gravity, and y diffusion term. Any questions? So these are the equations that are used to solve for fluid flow. We also typically write them in vector form to simplify the analysis. They are solved on a domain omega with a forcing term f. And we also express the divergence as div u to stress that it is an operator. The projection method works on a staggered grid. It takes the Navier-Stokes equations without the pressure, solves them without the pressure. U star minus un over delta t equal minus un dot nabla un plus nu del squared un. So all at time n computes a temporary velocity field u star, and then takes that u star and makes a Helmholtz decomposition. This is allowed because these fields, as we know, they form what we call polynomial rings. So we are allowed to do this kind of projection. Okay, if you're not familiar with the theory of manifolds, you can look that up. And we project on the manifold of divergence-free spaces. We compute the pressure, and we result in a Poisson equation for the pressure. We solve the pressure that allows us to get a divergence-free velocity. Now, this pressure is very expensive to solve. If you look in practice, some data if you look at the cost of, assume you have a CFD code. That CFD code has a pressure projection in it, okay? The cost, this plot shows the cost of the projection versus the rest of the calculation as we go high in computational cores. So as you go much higher to 10 to the 5 cores, the cost of the solver becomes dominant compared to the rest of the application, up to 80%, as you can see from this plot. And this gets worse when you combine this with Runge-Kutta methods, where with Runge-Kutta methods, you start with U hat I equal UN plus delta T summation J 1 to I minus 1 Aij F of Uj, where F is your right-hand side. You do the projection, and this is the equivalent of the projection. We use these idempotent operators, dg, that's divergence of the gradient. It's equivalent to the Laplacian when the grid is structured and staggered, because you have that combination. So the problem with Runge-Kutta method is that at each stage of the iteration, you have to do a projection. See here, pressure, 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 pressure. It becomes very, very expensive and more complicated. Now, one could ask then, how do we make these faster? Let's skip a projection. What happens if we skip a projection? Lee and Moyne in 1991 in their paper, An Improvement of Fractional Step Methods for the Incompressible Navier-Stokes Equations in the Journal of Computational Physics, page 90, volume 92, page 369 to 379, they say that they approximate the pressure phi2 with the previous value of the pressure. And then Capuano, Coppola, and Giotto, they became our friends after we analyzed their work. We are collaborating with them now. And their paper, Approximate Projection Method of the Incompressible Navier-Stokes Equations, in the AIAA journal, they came up with a higher order approximation. We wanted to understand how they came up with these approximations, so we developed our own theory, and we introduced in new parameters in the projection, this di and g phi tilde I. They are when we approximate or skip a projection. We also use the familiar theory of rooted trees, as given by this formula over there. I triggered the timer, so we were at like 2.5 minutes, okay? Then we go and apply this theory of rooted trees that allows us to express highly complex nonlinear right-hand sides. The trees allows us to get these elementary derivatives, which do not necessarily combine to total derivatives. So you start with u1 equal un, u tilde 2 is un plus a to 1 delta t, f of this this empty square that designates the projection, minus a to 1 delta t g phi tilde 2. And then, I can go through each one of those equations, but they will take time. I don't have time today. Then we come up with these a few lemmas about our new theory, and that first we designate the difference between the traditional method of the Runge-Kutta theory and our new proposed method. And we have these 3 lemmas that show how this is going to work. And finally, what matters is this theorem that we can skip a projection if we can show that this formula is equal to 0. So from this formula, you can obtain all of the phi tildes that are the approximation for the projection. And then when you can approximate the projection, you can use these approximations. The details are found in our 35-page journal paper. You're welcome to read it and do the analysis. And also, we find the general solution for these approximations given by also these rooted trees as summation of from j to k minus 1 gamma ij delta t to the j minus 1 q summation of f of tau. Now, these are the rooted trees, and we also need to approximate the pressure. So these are our approximations. They work for for RK3 and RK4, and this is a plot showing their stability. As you can see, the blue one is for forward Euler. The purple one is RK300. I'm trying to find the color to match it to the legend because it's hard to see. And then these are the convergence plots. And in conclusion, for this 8-minute talk, we can interpret the Navier-Stokes equations as a differential algebraic system of equations of index 2. With index reduction, the projection space manifold allows for non-characteristic approximations of the algebraic constraint that has to do with these polynomial rings. A theoretical framework for creating approximation to the pressure is provided. New formulas and approximations are shown, and verification studies are conducted for the order of accuracy. Thank you for your attention, and I leave the floor open for questions. It was so hard. I tried to make, anyway, okay. No, seriously, any questions? All right. Okay, so now I'm going to open my slides for a discussion. And let me actually move this window to Creston. Okay. So those are the slides of our discussion. I'm going to now work with you on putting together a list of what I did wrong in this talk. Okay. So give me a second so I can fit this to the slide. And I can hide, oops, I'll hide this guy. Okay, so what went wrong? What? No, seriously, just give me a second here. Let me move it back here, do the, oops, I'm moving all of them over there. Okay, I just need a list with bullet points. Okay, I just need a list with bullet points. I cannot see anything from here. All right, bullets, just bullet points, and we'll make the text color white. All right, so what went wrong? Let's talk, seriously. Lack of eye contact. Yes, because I was like frozen to the stupid slide, right? Okay, what else? Come on, give me some ideas. What did you hate about this talk?
On that same topic, the inflection of your voice didn't change a single time.
Okay, monotone. Voice, okay. Pardon me? No movement. Frozen, no movement.
A lot of hand wavy movement like this, and this little table.
Movements from far away, yeah.
It's far away than close
Yeah,
to
yeah. Okay. To tell you where we're looking at, right? Yeah, so dense slides, unfocused on a single idea. Okay, what else?
Figures
Figures?
the figures were pretty bad.
Yes.
Low quality in some.
Figures were bad, raster, low quality. What else? Too many equations. The equations were wrong, actually. So I was using scalar instead of vector. Okay. The equation quality was also bad. Did you notice the equations? They were like skewed and not like, yeah. Was bad, skewed. What were you saying, Maher?
Different formats.
Yes, different formats, different fonts, essentially, for different equations. Did you notice this?
Oh, I noticed that one of the slides was like incomplete. It was like click here to edit.
Yes, thank you. That's, where was it? Double click, yeah, double click to edit. Did you notice that one? Okay, so double click to edit. Okay, sloppy slides. Reading from slides. What? Pardon me? Long title, useless and boring. I didn't learn anything. Yeah, introduction was long.
You were also using a lot of filler words. A lot of filler words.
Yeah, filler words. So, like, I wasn't prepared. Yeah. Okay. Typos. Navier-Stokes, you know. That was like on the S&P 500, the Navier-Stokes. Yeah. What else?
References were too long.
And I read them, yes. Long refs and reading the refs. Okay, what else?
Figures were missing the axis title.
Yes. Okay, missing axes, titles, info. Okay.
Did you go over the whole agenda?
Agenda, oh my God, that's like my worst nightmare. I was having a hard time going through the agenda. Anyway. I didn't follow the agenda. Yeah. Okay. So the list is long, right? And It's funny, though, that you all know what goes wrong, that we all know. I'm not accusing you of anything. We all know what is crappy and what is bad in a talk when someone else is giving it. Yet, I challenge you to tell me that you don't do the same thing when you're up on stage and making a presentation. So if you recognize what doesn't work in a presentation, why do it in your own? Seriously. Like, have you asked yourself that? When I sat and asked myself this to become a better speaker, I'm like, yeah, what is wrong? What is holding me back? Now, that becomes a personal thing for you. It could be you're not used to the spotlight. Okay, well, change the lighting, man. Put the light on the audience and turn it off on you. Or turn off the lights on the audience and put the lights on you so that you don't see the audience. That's what worked for me, actually, for a long time. So mirror what you admire and reflect what you reject. All right. I want to focus today on what I think is a collection of useful tips for giving a great talk. In your PhDs, in your journey, in your career, there's this thing called the Pareto distribution in life, where you spend 20% of the effort, you get 80% of the results, right? And the rest is like point of diminishing returns. So it's the same applies in your research. You spend all of your time doing the research, yet the vast majority of your research is gonna be focused on communication. Whether you're writing papers, you're giving presentations, public seminars, talking to people on the bus, talking to colleagues. So you need to master your communication skills. That's the message here. The focus of this seminar is going to be a public seminar to a general audience. And trust me, you are going to be invited to do those. We will touch a little bit also on general technical conferences where you go to a conference like AICHE. You have people from all walks of life. And I guarantee you go into a presentation, into a room, there might be a couple of experts in your field, but the rest are the general audience. And I've always find it that I want to get everyone to be excited about what I'm talking about. So we will focus on a public general talk. And I like to distill the elements of a great talk. There's a lot more to this, so this is only a subset. And each of you knows more ideas, has more ideas, so we'll keep that open for discussion. But I like to split it into two things. In every talk, there's your content and there's your delivery. Okay? They're both equally important. I will focus a little bit more on the delivery because that's the one that usually requires a little bit more work for you to get better at delivering your message. Let's start with content. First, my recommendation is to use a minimalist design. Okay, now I did use a minimalist design in that first presentation, but I'm using another one here, but I like to use darker colors. Okay? There are scientific studies that show that in a public talk, use a darker color, you make your results stand out. They're a little brighter. Don't use like flashing white. Maybe use a slightly off-white, a light gray, or like this light green over here. Okay? Very simple. Do not overcrowd your slides. This is an image generated by ChatGPT about overcrowding slides with math and fluids. So I don't know what it thought. And then there's this greatest advice by Professor Sutherland who says, try to focus one idea per slide, one message per slide, one message, a single message, so that you can focus on one thing in that slide. If you look at my slides, usually a presentation, I have over 250 slides, and I go over those in 10 minutes. Well, 80 slides, and I can go over those in 10 minutes because I like to have one thing, one sentence, one plot per slide. Or you could do as Professor Sutherland does. He has 10 slides for the entire talk, but he could spend 5 minutes on one slide with like two drawings on it, okay? Next, pick a great title, especially if this is a public seminar. So, I'm going to focus here on a general seminar and a technical conference. So, general seminar, Don't be shy to pick a catchy title, man. Aren't you here for this reason? The worst talk of my life. Oh my God, this is interesting. I want to come here. Pick a catchy title. What are you going to lose? People are going to be excited about your talk. You're giving a public seminar, right? Now, context is going to be important. You know, I'm not saying you do this for maybe a very technical job interview. Okay, so be careful there. But again, for a general seminar where you have a wide audience, yeah, the sky is the limit. Pick a catchy title. If you're going to a technical conference, stay technical, but don't make it really nasty and fancy and filled with jargon. You can still deliver a reasonably technical talk to a technical audience who understands commonly understood things in your area without getting too sophisticated. So here are some examples. These are from actual seminars, okay, that I gave throughout the years. And I'm going to give you my first choice for the title and then the improved choice. This was given at the Colorado School of Mines, exploring the necessity of paradigm shifts and scalability enhancements in computational fluid dynamics for optimal utilization of contemporary heterogeneous supercomputing architectures. We've seen talks like this with titles like that, haven't we? Right? Check what I went with. Why CFD needs a facelift. Nobody's going to give a crap about heterogeneous supercomputing utilization. I put that in the abstract, man. Put it in the abstract, right? Why CFD needs a facelift? Why? Let's look at the abstract. In the abstract, I would put, in today's talk, we are going to address the changing landscape for computational fluid dynamics, right? And how heterogeneous architectures, et cetera, et cetera. Put it in the abstract. But this is a catchy title. People will come to it. Next. This one is my first seminar when I was hired as a faculty here, if you remember that. The first title was An In-Depth Analysis of Truncation Error-Induced Numerical Dispersion and Dissipation, Exploring the, and I put a subtitle too, Exploring the Challenges and Frustrations in Computational Fluid Dynamics. Or, Why Do Computational Scientists Complain? Now notice I'm asking a question, right? So that triggers something like, I want to know why. I want to know why. Why do they complain, right? And so, do something like that. All right. This one for the COVID stuff. So we gave a lot of talks on that. And one could go, computational fluid dynamics-based simulation, strategic reconfiguration of the Utah Symphony environment for enhanced COVID-19, assessing airflow and viral transmission. I mean, yeah, sure. This is what we went with. The Utah Symphony reimagined using CFD. People like that. There's a general, that was the first time we were actually touching with the public health, with the public. People wanted to learn about this. So you gotta come up with a nice title to communicate your message. This could work for a paper, for your specific journal paper. I'm not saying use this for your papers, right? But for a general talk, yeah, do that. Or ask a question, can an orchestra keep its doors open during a pandemic? That's a reasonable question. That's something, look, I haven't thought about that. I want to go and see, right? I'm not giving them the answer. Finally, deliberate demonstration of ineffective public speaking techniques and intentionally poorly executed presentation to illustrate common pitfalls, etc. So that's this talk. That's the worst talk of my life, right? Okay. Here are some tips to picking a great title. Keep it short and sweet, like 10 words. Use clear and descriptive language. Get rid of jargon. Incorporate action verbs like choosing, transforming, making, creating. Use action verbs, okay? Ask a provocative question. You know, what if we could live in Mars? Can the Utah Symphony remain open in a pandemic? Why do computer scientists complain? Use numbers or lists like 5 strategies to give a great talk so you know what you're getting out. People know what they're getting out. 5 ways of weighing cells, right? So something like that. Sorry, I don't mean to pick on you, but like it just occurred to me, right? So I promise a story, why I became an engineer or growing up in a civil war, something like that, right? Highlight the benefit, mastering public speaking in 3 easy steps, and create intrigue, right? Something intriguing, the worst talk of my life. Like, I'm intrigued by that. Okay, next, no agendas, please. No agendas, absolutely whatsoever. Agendas are for meetings. The next time you watch a movie, do you look up like, oh, you first like, okay, what is going to happen next? Or when you pick up a book, do you spend an hour reading the table of contents? You just hit the ground running, right? Because you want to read the story. A talk, you're telling a story. Instead of agendas, however, I have a better idea, a much better idea. Start at the end. Show them your results first. Show them your results first. Or wet their beak, so to speak. And speaking of rhymes, a statement that rhymes, a statement about your results that rhymes is more likely to stick in people's minds. As they leave, they're going to be like, oh yeah, you know. So here are some examples. From my numerical methods class, when in doubt, print it out. To this day, my numerical methods students, when they see me, when in doubt, print it out. Because they're programming in Python, okay? And they're like, oh, what is my code doing? I'm like, when in doubt, print it out, okay? For the COVID-19 study, if you change the airflow, you change where the viruses go, okay? So that was an easy public message that everyone left remembering this word, okay? Another one, when data is in hand, plot it to understand. So that's the first thing I tell my numerical methods students, is like, you're faced with data. What do you do with it? Just plot it. Let's see what it does. Just plot it before you do anything about it. That will allow you to visually inspect it. You see the outliers. You see what it's trying to tell, okay? Use analogies. The greatest communicators in science, they use analogies. Like, this is equivalent to 1,000 elephants. This pressure is equivalent to 1,000 elephants standing on a car. Oh man, that's a lot, right? So here's an example with our COVID study. Actual numbers, the CPU time for our COVID studies was about 600,000 CPU hours on a 1,200 node cluster. Does anybody know what that even means? What the heck is a CPU hour? Okay, so here's what we said. Then we said that's the equivalent of a single computer running these calculations for 52 years. Now that analogy, people will understand. So think about analogies. Every time you have an important result, make an analogy. Like use cars, elephants, lions, stadiums, capacity of a stadium, things like that. Okay. Now, if you need to use math, use it wisely and cleanly. Okay. In our work, there's a lot of math. And trust me, it's hard to get by, but I do get by. I just went to a national conference, and I used just a few equations and communicated the entire message, okay? So use native vector. At least if you're using math, use it well, okay? Don't take screenshots from the papers because you're lazy, you don't want to type it. This is what I did here. I took screenshots from papers without even thinking, oh, this is not a vector, this is not a vector, this is a vector. What the heck am I writing here? Take a minute and write the equation down. Or at least if you want to screenshot it at a high quality. And don't squish it like this. If you can't see that this is squished, try to see it now. Compare this equation to that equation. Okay? This is slanted, squished, and it's pixelated. Now this is the one that drives me nuts. When you see a math equation, all italics. If you look at journal specs, if you look at old manuscripts, like even from the days of Euler, you will recognize that only variables and unknowns are italicized. Everything else is not in italics. Function names are not in italics. Subscripts that designate words like wall or air, they're not italics. So why italicize them? Let me give you an example. Sometimes I see something like this, A cosine X. I'm like, to me or to a computer, this could read A times C times O times S times X. Why is this sign not S times I times N? Why? Just because you see the clustering of words, you think it's sine? Whereas the right way of doing it, yes, there is a right way of doing it, is the name of the function is a proper name. Don't italicize it. If you're using LaTeX, that's \sign, okay? I don't know why I have a guitar here, but okay. So subscripts, T left wall, or like sometimes T left wall on the outside, or and it's all italics. Well, left wall is a word, right? It designates, it's a sentence. Don't italicize it. T wall, TW, is W a variable? No, this is a fixed thing at the, T is the variable at the wall. Now TI here, I is an index. It's a variable, T0, T1, so I keep it italics. I insist on destroying this thing. Okay, let's put it here. Okay. Now, this is non-generic, but some journals prefer this, some don't. With dimensionless numbers, I do not italicize them. Many of the top quality journals do not italicize them. I think they're more stylish if you don't italicize the dimensionless numbers because they are like parameters. They're not variables, right? They're kind of set by the flow. But you can also argue that, you know, they could change. So you can, again, the problem is like EU. Is this E times U? No, it's the Euler number, right? So it should not be italicized. It's a word. Okay, worst thing ever. You need to distinguish between the difference between a raster plot and a vector plot. A vector plot is like the font you type on your Microsoft Word. You zoom into infinity and it will still look crisp and perfect. A raster plot is just a bunch of pixels. You zoom in a little bit, you lose the quality. There is no reason in this day and age to put raster plots unless you're actually taking a picture of your plot. Okay? So for example, crappy plot, good quality plot. Okay? Crappy figure, good quality figure. I drew this figure on my computer. Why am I turning it into this if I can get it like this? So always export as scalable vector graphics or PDF. Don't export as PNG, JPEG, or TIFF, even if those are high quality. The only exception I make is if my export has so much complexity. Like I was working with Ariana the other day on a visual syllabus for our course, Numerical Methods. And there's some really complex gradients in color, and the PDF couldn't handle that. So we had to export instead as a very high quality PNG, but that was like an exception, right? There's no reason to do otherwise. Okay? Now, do not rely on color to designate results with different parameters. Oh my gosh, the many times I've seen this, they put like a little legend over there and they blast you with color. Like if this were 2 curves, that's fine. But if you had 15 curves, this is ridiculous. Instead, use symbols and even don't rely on symbols. Annotate. Oh, look at that. This is the 0, 0 case, 1, 0, 0, 0. Oh, okay. I get it. Just put an annotation. You don't know how to do it in MATLAB or Python, just do it by hand in Canvas or Keynote, whatever. Okay? The other thing is pie chart, and that's even worse. Pie charts with 15 colors, but a legend. Like, just put the names on them, or combine the colors. Maybe your categories are too specific. Broaden your categories. Make it 3, 4 colors maximum. Okay. Delivery. And this is kind of what I really want to drive here. Treat every talk as if it is the most important talk of your life yet. This is your reputation on the line. Okay? You give one talk, you can get people leaving like, man, I love this talk. I love it. That's great. Okay? In a way, your reputation is on the line. So, when you give a talk, you take on the stage. You are putting on a show. That's at least my opinion. Even my lectures, I treat them like this. So my students know, like I dim the lights, I start with music, you know, it's like putting on a show, right? It's not a Broadway show, but you know what? Because I think a little bit of entertainment when you're sending a message has a more likelihood of delivering that message. Now, we're always assuming that your work stands on its own merit. There is scientific papers behind it, etc. This is only about the communication of that. Okay? So, avoid using a tablet. Your talk needs to come from your heart. Now, for long talks, I get it. You need to get like some notes somehow. Maybe put the tablet over here and glance at it. But try to avoid walking and looking at the tablet, okay? Unless you're teaching a class, right? That's different. This is a public talk, again. Do not read the slides. Do not even read the presenter notes. Now, I'm reading the slides. Why? Because I'm teaching you something now, okay? So this is different. When you're teaching, it's a different story. Yeah, you can read from the slides. You work with the students. You catch a typo. Presenter notes, again, are not journal articles. Like, don't stand here and like, what did I write here? And you're scrolling through the presenter notes. But like, if you follow James's advice, you put one idea per slide. You deliver one bullet point. You put that in your notes. Say, remember to talk about how I went bald. Oh, throw a joke about yourself. People will connect with you. They know you're human. Okay. Now you need to be motivating. I cannot stress that enough. You need to be excited about your work. If you're not excited about your work, nobody is going to be excited about your work. In fact, you need to be motivating enough that people on your way out, they're going to tell you, please start a church, right? Okay. Don't be a one-chord wonder. Now that's when this comes in. Okay? So this is my fancy flamenco guitar. Let's see if I still play. And I always wanted to do this, like like in the movies, drop the notes. This is Asturias, a beautiful piece by Ishaq Albeniz. If you Google it. So imagine you get invited to a party. Imagine you get invited to a party, and you come, and you're like, what? Welcome to the Hotel California. It's a lovely place. Right? You don't do that. That's going to be boring. Right? So who said being monotonic? You mentioned that, right? So don't be a one-chord wonder. Instead, like, play something cool. Right? People will love that. So don't be a one-chord wonder. Make your voice play the full melody. Now, I'm doing the litmus test. I'm trying to leave you with messages. Right? Okay. Don't be a statue at the podium. Also, you guys also mentioned that. I'm standing frozen here. Animate your words with your action. So move around. Move around. Two things happen. You move around, people get focused on you. They listen to you. They actually will listen to you. And you don't fall asleep. So yesterday, I was telling Ariana that I was so tired before lecture. Once I hit the stage, I started walking, I got that adrenaline pumping, and I woke up. And I felt better, okay? So be like this pigeon, walking all over the place, maybe having a bad call, but... So then I went ahead and I tried to gauge, I have some videos from my lectures, and I tried to get an idea of a histogram of where I am located. So on the y-axis, you're looking at the probability of me being positioned between the podium and the slides. This is your distribution. You need to be more likely present near your slides than in between the podium and the slides, a little bit on the podium where you go and advance. That's why I don't use a clicker. In the new class, I'm teaching numerical methods. There's 50 feet between the projector screen and my laptop. I'm walking left and right. I'm walking left and right. And the students are frozen on me. And I would refuse to use a clicker. You use one. It's up to you. It's your style, right? But not using a clicker forces me to move around. You move around, you interact with the audience. Okay? And finally, be inspired by the great speakers. That's what inspired me. If you've ever listened to Carl Sagan, blow your mind. The greatest educator of all time. An astronomer and public science educator. The guy's a miracle. Richard Feynman, look at him, standing here, like telling the students like that, instead of like standing over there, pushing the notes, right? Move around. Use your arms, right? Neil deGrasse Tyson, Jim Al-Khalili, even Steve Jobs. Very theatrical, right? Now, I'm not saying be a salesman, right? But try to incorporate some passion, some motion into your slides, and that's it. 11:30. Okay. Thank you. Okay. If you want to see the improved talk, I'm happy to show it, to demonstrate, but I get it.
Let's do it.
Should be 8 minutes only. All right. So this is the talk I gave at the Division of Fluid Dynamics conference. Okay. So I'm standing here, and the speaker comes and introduces me. Professor Tony Saad is going to talk to us about fast projection methods, etc. And I'm standing there. People have a minute. They read the title. They read my name. They read the whatever. I don't need to read any of this. And in fact, I won't. Okay. Well, thank you, Professor, for introducing me. Imagine you have a method where you can do DNS level calculations, very high fidelity calculations of fluid dynamics at half the cost. What I'm showing here is one of our results for a three-dimensional turbulent jet. The first one is using conventional method. Took about 16 hours on a big cluster. And the second one is using our proposed method. Took 8 hours on a cluster. Okay? I'm going to tell you about that today. If you are a CFD practitioner, you know that computing the pressure is the most expensive piece in a conventional CFD calculation. So see, this is my motivation and background, right? So I started with the results from the end, and I'm going to do this. So excuse me, I'm going to read the slides a little bit because I didn't practice this well enough. Now, to motivate you, I'm going to give you an example. This was in 2020. The Utah Symphony came to our team and said, can you help us study COVID spread on the orchestra stage? We're like, yeah, absolutely. We can do CFD for that. So we went ahead and did some calculations. We helped. We figured out what's going on. We figured out what's bad, what's good. We concluded that they need to open the doors and rearrange the orchestra. You can find the details of the study in these papers. However, those calculations were so expensive. They cost us about $14,000 if you were to put a dollar amount on the calculation time. Because when you run on a computer cluster, there's an intangible cost that you're not seeing. You know, there's the cost of electricity, the cost of maintenance, the cost of air conditioning and ventilation. And most of that cost was consumed by the pressure, which for those studies consumed over 41% of the calculation. So that's just about $5,500, the amount of your Roth IRA. An analogy, okay? Analogy. Now, this gets even worse at large scale. So that's the same plot I used before, but I'm presenting it in a different context. If you were to plot or to analyze the fraction spent in the pressure solver compared to everything else in your code, and just take this to an extremely high, fast supercomputer. So on the x-axis, you see I'm increasing the number of cores, the number of CPUs. You see that it exponentially increases. The cost of the pressure solver exponentially increases, reaching over 80%. And that's well-known fact because it has to do with all-to-all communication between the compute nodes, which is required by the pressure. This gets worse when you add high accuracy, such as Runge-Kutta methods. So the audience is technical. They know that they know what Runge-Kutta methods are. Where at every stage, you have to do a pressure solve. So there is a need to speed up pressure solvers or avoid them altogether. We always thought that there's no free lunch. If you were to plot the computational cost versus accuracy and fidelity, typically, as accuracy goes up, so does cost. So for example, on the lower left here, you have these low-order, fast response, potential flow models, very, very fast, just mass conservation models. They're very cheap, but they're very low accuracy. Compare that to the upper right, where you have direct numerical simulation, the most expensive tool, the most accurate tool we have for simulating fluid flows. It's very expensive, but it gives us the most fidelity. We want to be here. be great if we can have high fidelity but at a lower cost. Okay? And that's what we're trying to work on. At least we have a head start. Our hypothesis is that it is possible to replace the pressure solve with suitable and cheap approximations without sacrificing accuracy or stability. So I forgot to mention that it's good to have a hypothesis in your even if it's a small presentation. At least put one little hypothesis. Okay? So you can help them understand, help the audience understand what you're trying to do. Now, this should naturally result in cheaper high-fidelity Navier-Stokes solvers because we're skipping projections. Speaking of projection, I'll just remind you what it is. If you take the full Navier-Stokes equations, don't worry what they are. They're just complex equations, 3 momentum equations and a mass conservation equation. If we write them in our mathematical form, I want you to focus on this gradient of the pressure over here, this GP term. Okay? The projection method says, well, we don't have an equation for the pressure, so how can you solve for the pressure? You only have equations for the velocity. So we do what we call a projection. First, we solve the Navier-Stokes equations without the pressure. We get a velocity field that doesn't conserve mass. And then we solve for the pressure. We use the pressure to enforce mass conservation. It's a little trick called the Helmholtz decomposition. It's a well-known thing. Okay? You're familiar with it, but that's the pictorial depiction of the projection method. Now, every time you see this vertical arrow, know that that's a costly thing to do. Okay? Our objective is to avoid these costly arrows. And in 1991, to the best of our knowledge, the first people who looked at this were Lee and Moyne. Moyne is everywhere in CFD. Well, you notice here they dropped one of those vertical arrows, and instead they replaced the pressure here with an approximation using the old pressure. And it worked. Indeed, we've demonstrated that it actually works and gives you second-order accuracy as they claimed. Then in 2016, coincidentally, when we were first thinking about this, Capuano and Coppola and their co-authors, they extended the method for a third-order Runge-Kutta. So it gives us better order in time. And notice how they skipped these 2 vertical lines here. So it's cheaper. You think like, yeah, it's probably going to be 30%, 60% cheaper maybe. Okay? But nobody knew why. Those were just ad hoc approximations as far as we know. So we set out to build a framework to untangle and analyze all of this. The first thing we did is that for any Runge-Kutta method, we added a switch. What if, in some cases, you want to project at stage 1, skip a projection on stage 2, project at stage 3? What would happen? Would you improve stability? Would it affect accuracy? So generalize that idea instead of skipping all projections. This is a conventional Runge-Kutta method. What matters here is comparing the proposed method with the conventional method. So we keep that first equation the same, but the second equation that contains this pressure term, we're going to modify it a little bit. Look what we did here. We added this switch, this knob, to turn on or off a projection. If the projection is turned on, we don't have an approximation. If the projection is turned off, then D is 0, then we have an approximation over here. Now our objective is to find those approximations, okay, which are unknown. So how do we find those approximations? We first develop an analytical version of our numerical method. That's weird, right? Well, our numerical method is an algorithm in math. We can write the math for it. So we develop an analytical version of the math of our algorithm and compare that with the analytical version of the exact solution. Okay? Well, if we have an exact solution, why do you need a numerical version? Well, no. This exact solution is just a Taylor series. We really can't solve an infinite number of terms. But at least it tells us what's going on. Okay? And that defines what we call a truncation error. From that, we can do all of this math. In our 35-page paper, you can look at all of that. And finally, we are able to find approximations that look like this. Okay? Now we got to the punchline. Okay? So we found these approximations. For RK2, they're simple. They're just like the one that was discovered by Lee and Moyne. For RK3, we discovered an infinite number of solutions. Okay? Compared to the one solution that was found in the literature, we discovered an infinite number of solutions. And remember, there are 3 variants because there are 2 stages in the RK, and there's 2 DI. In the RK3, there's like 0, 0, 0, 1, and 1, 0. So we project second stage, project third stage, don't project at all. These are the approximations, right? They're very easy to implement. You put them in your code. We demonstrated order of accuracy. So this technical conference, they know some of this. This was not a general audience like here, but at the technical conference, they know what order of accuracy is. They've seen these plots, so that's very familiar to them. The cool one is the RK4 method, which was the first to be done in the literature. We have 7 variants, and we also have an infinite number of solutions. There are parameters that we can tune. We're now studying the impact of those parameters on improving stability and energy conservation properties. And finally, we were able to estimate the cost of these methods. So what you're looking here, I want you to focus on this plot over here for RK3. We are showing the potential cost savings. You throw this new RK method into a code. There's a fraction of it that you spend on the pressure, and the other fraction you spend on other things. Now, those other things, like if you're adding radiation, for example, that fraction grows and the fraction of the pressure shrinks. Or in the simplest case scenario, we're just doing pure fluid flow, the fraction of the pressure was about 41%. So that's the best case scenario. So what I'm showing here is for these different values of the fraction of the pressure, that's gamma. For gamma 0, essentially, the pressure dominates your simulation. Gamma is 25. The pressure dominates your simulation. Over here, pressure is 75%, and so on. And you see that we are overperforming compared to the traditional methods versus the cell-Reynolds number. Now, the cell-Reynolds number tells you how accurate you are in space, right? And the smaller your grid resolution, the closer you are to DNS. We beat the conventional methods for every value of those gammas, even at infinity. Even in that worst case, we're still a little bit, maybe even 1% better. So that means, and a gamma equal infinity means the pressure is insignificant in terms of your other calculations. That would be like very complex multi-physics calculation, unrealistic. But in reality, we are somewhere around here. So our methods could be 40% cheaper, 50% cheaper than conventional methods. Final thoughts, instead of conclusions, final thoughts. Thoughts about what's going on. There's still a lot more to do. Maher is doing all of that now. There's still a lot to do going forward. These can be very advantageous for DNS, which is something we hadn't thought about before, but kind of realized recently. And I thank you for your attention and questions. All right, thank you. Okay.